Okay, now that we've looked at the equation to find your speed and your velocity, remember your speed is your distance over your time, your velocity is your displacement over your time. Distance, remember, is looking at how far you've traveled. Displacement is looking at how far you've traveled from your starting position to your ending position, and it must be in a straight line. Now we're going to look at graphs. So within this unit of kinematics, you have to be able to explain things in words, graphs, and equations. Okay, so all three are going to be tested at the end of the unit. So the first type of graph we're going to look at is your displacement versus time graph. For your displacement versus time graph, you'll notice that your displacement is on the y-axis. Sometimes it'll say distance. Sometimes it'll say position. It just depends upon what you're looking at. Always be careful to check your units. Time will go on the x-axis. Okay. Time is almost always on the horizontal axis. In physics, okay, that would be looking at your independent variable as you go through it. So what you're going to be looking at is talking about how the object is moving. So if you look at time 0, 0, I would sketch this graph in your notes so that way you have something to refer back to. We're going to look at it in greater detail. But you'll notice from 0 till about 3 seconds, you're moving away from the origin. So you're moving in a positive direction. If you look at your line, it's moving positively. Then from about 3 seconds to 5 seconds, your displacement is not changing, so that means you're standing still. Then from 5 seconds all the way up about 7 seconds during that time frame, your position increases a lot, so you're covering a lot more distance during this time frame than you did initially. Then again from 7 to 8 seconds, you're at rest, you're not moving, and then at 8 seconds, now you turn around and you go backwards really fast all the way back down to a 0. So this is telling you that if you looked at your total displacement from start to finish, look at your position. You started at 0, you ended at 0, so your total displacement for the whole thing would be 0. If you looked at it in individual segments, you would have displacement, but across the entire thing, you would have no displacement. Okay. The next thing that you look at is your velocity versus time graphs. Okay, so with your velocity versus time graph, now your velocity is on the y-axis, time is still on the x-axis. Okay, so we're keeping those consistent. Velocity here we have measured in meters per second. They put Vx here. You don't have to worry about that. That's just telling you you're just moving in the horizontal direction. It's not a big deal right now. Velocity is always measured in meters per second. And then your time is going to be measured in seconds. Okay, so on this graph, if you look at it, you're traveling at 4 meters per second. So you're moving at a constant speed for 2 seconds. You're just traveling at 4. So you're walking at a steady beat. So if you're in band, this would be you're just marching to like a steady drum beat. If you were thinking about it in your car, you would be driving on cruise control. Okay, so you're not speeding up, you're not slowing down. Then at 2 seconds, look at your speed. It starts to approach 0. So you would be slowing down, okay, as you go through this. Okay, the next thing that we have to look at is our slope. Whenever you're looking at graphs, slope is extremely important that you look at it. So if you remember from your math classes, slope is rise over run or delta y over delta x. Your slope equation, equation of a line, y equals mx plus b. So if you look at this model and you do slope is rise over run, your rise on your distance versus time graph, your rise would be your distance, your run would be your x-axis, which would be your time. So you would end up with delta x over delta t. Delta x over delta t is your velocity. So when you have a distance versus time graph, okay, again, this is looking at distance versus time graph. What quantity is represented by the slope? I just told you that. That's your velocity. What quantity is represented by the y-axis or the rise? That would be your displacement. And then what quantity is represented by your x-axis or the run? That would be your time. Okay, so another way that you can use to find your velocity is your slope. Okay, and you'll do some activities and problems where you have to do this. All right, so I told you to sketch that graph at the beginning. Okay, this is the exact same graph that was on the first slide. Okay, so if you wanted to figure out what is the velocity of the object from 0 to 3 seconds, you're just looking for the slope. So you would look at your rise. Your rise is 30. Your run would be 3 seconds since it says from 0 to 3 seconds. So it would be 30 over 3, which would be 10 meters per second. Okay, so that's all you have to do. If you look at your next time frame, okay, going from 3 seconds to about 5 seconds, look at your rise. There is no rise, so it would be 0 over 2, which is why your velocity at this point is 0. So you've stopped moving. Okay. Again, remember the velocity is your slope of a distance versus time. It could say distance versus time, displacement versus time, position versus time. All of those are going to be looking at that meters. So anytime you have meters on the y-axis, seconds on the x-axis, you're looking at the velocity. Okay, you could also, again, find the velocity from 7 to 8 seconds. Okay, if you do 7 to 8 seconds, again, look at your rise. There isn't one. Okay, you're not going anywhere. So your velocity is 0 meters per second. So that just means that the object has literally stopped. Okay, so you haven't got anywhere. Your car's on its brakes. Okay, you're just not moving. Okay, you could also do your velocity for the last part, the 8 to 10 seconds. Remember that since you're looking at your velocity, it's always looking at the change in distance over time. So your final would be 0. Your initial would be that position that you're at to start with, which would be 90. And then you're doing your time, the change in time, 10 to 8. 8 would be 2. So your slope would be negative 45 meters per second, which means that you are moving backwards. Okay, so now you're moving back towards the origin, or you're heading south, whichever way you want to think about it, but you're heading back to where you originally started from. Okay, as you go through it. All right, so real quick, I want you to try sketch this in your notes, this picture, this graph. So I'll give you a second to make a quick sketch, and then we're going to talk about the motion during each of these time frames. But go ahead and sketch this graph. It doesn't have to be too specific. It just has to be a quick sketch mostly. You don't have to worry about your displacement. I'm not going to have you do like a calculation of the velocity. I just want to talk about the motion and as you're moving. Okay, so if you look at it from 0 to 9 seconds, okay, so during this first time frame, you'll notice that your line is a curve. Okay, and if you look at your slope, is your slope getting steeper or flatter? If you look at your slope, look at a line tangent to your line, you'll notice that your slope is getting steeper. Remember that the slope of a distance versus time graph is velocity. Since your slope is getting steeper, that means your velocity is increasing. Okay, again, I'm not asking you to figure out what it actually is. You could, but at least this way you know that it's increasing. Okay, and then from 9 to 11 seconds, so you're talking about this area, this flat section right here, I just said that it's flat. So again, looking at your rise over your run, your velocity is 0. So your object is stationary, at rest, whatever word you want to use. Say it stopped for 2 seconds, something like that. Then if you look at it from 11 to 15 section, from this 11 to 15 seconds, look again at your slope. Now you have a nice constant slope. So your slope is constant and positive. If your slope is positive, that means your velocity is positive, which means you're moving in the positive direction. So you're moving in the positive direction at a constant speed. Okay, and then the last part is from 15 to 17 seconds. So during this really steep section right here, your slope is constant and negative. So this would be looking at this part of the slope. Okay, so now you're moving backwards again. If you look at your slope here, your slope is really, really steep. That extreme steep slope is going to tell you that you're moving really, really fast. Okay, the slope is constant, so it's still a constant speed, but it's a fast constant speed. So whatever speed you were moving at from this 11 to 15 seconds, now you're moving even faster. Okay, but again, you're moving now south or in the negative direction. South, west, whichever way you want to say it, but in a negative direction. Okay, look at your homework packet at number 17. And again, I want you to take a moment to go through those. You have a position versus time graph that you're looking at. A is up here on the top. B is this angled line. C is on there as well. Okay, D and E. So go through there and answer those questions. Okay, C is actually this like curved line that you're looking at. D is this sloped line. It's going negative. And then E is this bottom line down here. Your x-axis, sorry it's not real clear in the picture, is this horizontal line close to where it says time. So C is looking at the curved line, not the straight line. Time would be that horizontal line right there in the middle. So go through that, try to figure out which one has constant velocity, accelerates, changes direction, not moving, fastest constant, slowest constant, and greatest acceleration. And then we'll go over those in just a minute. Alright, so if you look at part A wants to know which one maintains a constant velocity. So you're looking at a position versus time graph. So for a constant velocity, you're looking for something that has a steady slope. Okay, so B and D. B has a positive slope. Okay, still a constant velocity. And then D also has a constant but a negative velocity. You could also argue A and E, however, A and E's constant velocity would be 0. So I guess a better way to phrase question A would be maintains a constant non-zero velocity. So anytime we're really talking about constant velocity, we still want the object to be moving. So B and D are what we're looking at. I did not say constant positive or constant negative, so that's why B and D are both your answers, because one is moving positively constant, one of them is moving negatively constant. Yes, even though they cross the x-axis, that is irrelevant because you're looking at the slope of the line. Which one accelerates? That would be which one has an increase in velocity. Okay, if you think about it in your car, if you hit the gas pedal, you're hitting the accelerator, and you watch your speedometer go up. Okay, so the only one that is accelerating would be C. It has that curved line, so your slope is getting steeper and steeper and steeper. When you're looking at which one changes directions, that would be none. Okay, in order to change directions, you have to have that that mountaintop. Okay, like the last ones did, where you were going in the positive direction, then you turned around and went in the negative direction. If you look at B, B is starting below the x-axis, so this means that it's starting in the south region. It's going towards the x-axis, so it's heading north. It passes the origin, and then it continues going north. But the entire time, it's heading north. All you're saying is that it started behind whatever point of reference you started with. If you look at D, you're starting in front of the reference point, heading south. So you're sitting there heading south, 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 and then you hit your reference point, but you're still going south. Sorry, my clock, I'm filming this at home, and my clock's going to go off now. I apologize about that. It goes off on the hour, every hour, as long as it's daylight. So, sorry about that. For part D, which one is not moving? The two that are not moving are going to be your constant horizontal lines, which would be A and E. Which one has the fastest constant velocity? For fastest constant velocity, you're looking for the steepest slope, which would be B. For F, again, you're looking at which is the slowest constant velocity. Again, slowest non-zero constant velocity, so that would be D, because it is the flattest esque line that's not a straight horizontal. And then which one has the greatest acceleration? That would be C, because it is the only one that is accelerating. Okay. Now what y'all are going to do, again, I apologize about the clock. I forgot. I wasn't watching my time very well. Now what y'all are going to do is you are going to go through and actually rank some of these graphs. So each group is going to get a sheet of paper. You're just going to do them as a group, as your table. There are 6 graphs, and you're going to rank them in order of distance and displacement from least to greatest. So you'll do it once for distance and rank them least to greatest, and then you'll do displacement least to greatest. So you'll have to have 2 sets of rankings, and then y'all will discuss and talk about those answers.